Hello, so my name is Sylvain Munaut, and I'm here to talk to you about GSM and how you can attack it with very cheap hardware. So I'll start with a short introduction about GSM so you can understand what I'm talking about. Then directly to the IMSI Detach denial of service, and then how you can implement a passive listener with a simple mobile phone. So a few words about me. I have a background in computer science, and I'm generally interested in everything low level, and I've been working with GSM for about 2 years, but more specifically the last year where I've been active in OpenBSC and Osmocom-BB. So this is what a GSM network looks like, at least a plain 2G network, voice only. So on the left you have the mobile station, basically the cell phone that communicates over the air to what's called the BTS, which is the base transceiver station. This is really just the transceiver. It doesn't have much logic into it. And then a BSC, base station controller, controls several BTS grouped into what's called a location area. It's just several BTS grouped together. And then the MSC controls several BSC. And the elements that we're interested in here is for the denial of service, we will inject packets onto the air interface, and they will go transparently up to the MSC. The BTS and BSC will just transfer them without interacting. And of course, to sniff phones in the vicinity, we'll just listen to the air interface. So this is what the GSM protocol stack looks like. So at layer 1, you have what's called the physical layer, then the data link layer, which is called LAPDM, but we won't talk about this here. And then finally, the highest level is layer 3, which implements all the various control. So on the air interface, it's split in several bands, as you probably know, like GSM 900 and DCS and PCS, things like that. And each of those bands has 2 sub-bands, I would say. One is reserved for downlink, that is all information going from the network to the mobile station, and then another sub-band for uplink, everything sent by the phone to the network. And what's called an ARFCN is basically a pair of frequency, one in the uplink and one on the downlink. Okay, on those frequency, the information is transmitted by bursts, and there are 4 main types of bursts, but 3 of them are really for special functions, and only what's called the normal burst transmit real data and information, and this is what we want. Those bursts are not transmitted. Are transmitted synchronously, completely. It's a full TDMA system, and so some people described it as a nightmare because you have like TDMA inside TDMA. It's very complicated. But for our purposes, what we need to know is that one frame is 8 time slots, and each time slot is a burst. And what's called a physical channel is 1 time slot on one particular RFCN, so on one particular pair of frequency. Up to layer 3 now, we'll skip layer 2. It's subdivided again, and the lowest layer, which is called radio resource management, RR, basically establishes point-to-point connections. And what we really want to know is like the upper layer, which is called MM, for mobility management. This is what we will exploit in the IMSI Detach trick. And its main function is basically to track the user. It tries to answer one simple question, which is, okay, I want to contact this user. What location area is that user in? It also ensures like user confidentiality, things like that. But to accomplish this goal, it uses 2 main procedures. What's called the location update. This procedure is used in 3 separate cases. First, when you turn on your mobile phone, like you log into the network, or when you change location area, so you basically tell the network, okay, I moved from this location area to that other location area, or what's called a periodic update. Basically, without any reason, I'd say your phone will just contact the BTS to say, okay, I'm still here. The other procedure is IMSI Detach, and that's basically the log off of the network, saying to the network, okay, I'm turning off my phone, don't try to contact me anymore. Okay, so the denial of service itself. Almost all procedures in the network will be authenticated and ciphered in a real network at least. The example on the left is the location update, for example, and you see the first step here is like the establishment of a point-to-point connection. Then the phone requests a location update, and then the network authenticates, starts ciphering, and then proceeds into effectively doing the location update. Then the channel is released. The problem with IMSI Detach is that the specification doesn't allow for ciphering or authentication at this stage. So you just open a channel, you say, okay, log me off the network, here is my identity, and you're automatically logged off without any kind of verifications. And of course, that's kind of a problem. So how do you exploit it? Well, it's pretty easy. You just open a channel, send an IMSI Detach indication message with the IMSI, which is the like the serial number of the subscriber that you want to log off the network. And a year ago, that would have been pretty hard to do, but with Osmocom-BB now, we can just take the layer 1 and implement it on a simple mobile phone and send the message. It's really, really easy to do. I implemented it in like 15 minutes yesterday. It works just great. So what does it do exactly in the network? So the IMSI Detach indication will be sent up to the MSC, and the MSC will mark that subscriber as detached. What this means is, for mobile terminated services, that is, if you're trying to call the target, you will get a message like, okay, this user is outside of the coverage area, or something like that, because for the network, this user isn't connected. For the user itself, if he tries to place a call, it will work, because it will send a message, okay, I want to call that number, and the network will respond, okay, but you're not logged in, so please log in first, and it will then re-log in, and the call will proceed. It will just take a while longer, because you have to do much more work. The spec says that, in theory, the MSC should terminate all MM connections. That is, if a connection is currently active, it should shut it down immediately. This seems to depend on the network. On my home network, like in Belgium, that's what it does. If I send an IMSI Detach while I'm in a call, the connection is like cut instantly. Here on T-Mobile, it just does nothing. So apparently, this depends on the network. An interesting side effect of the fact that you force a new location update request is that it can help you uncover the relation between the IMSI and the TIMSI. So basically, when you log into the network, to try to hide your identity, the network gives you a temporary ID, which is only valid in that particular location area, and that's what's supposed to ensure confidentiality. But since you can force to the renegotiation, you can actually uncover the relation between the two. And also, since you create more control traffic, that's good, because, at least, well, good for an attacker, because control traffic means lots of known plain text, which is great if you want to break the ciphering key. And the ciphering key will probably be the same for the subsequent voice call, so you don't even have to crack it again. The operator can actually defend pretty easily against that, because IMSI Detach is an optional procedure. What I mean optional is that the network can use it or not. So since it's optional, just don't use it. Of course, you have to make sure that if you don't use it, you actually ignore all incoming IMSI Detach indication, else it's just useless. It's not free, because basically if a user logs off, you don't know that he's not on the network, so you will try to contact him for nothing. To try to track the user, you can use the periodic location update. That is, you force the phone to periodically ping the network, but this comes as a cost as well. since the phone will use some control channel for some time. So it's basically a trade-off between useless paging traffic and almost useless location updating request traffic. So that just shows you can do. Something else you can do is just refuse incoming IMSI detach where the identity is specified by IMSI. So in the IMSI detach indication message, you can either detach a specific IMSI or a specific TIMSI. So either with the identity, the global identity of the subscriber or its temporary identity. Since he is logged in onto the network, he has a TIMSI. So you should only accept incoming IMSI detach when they're specified by TIMSI. And all phones I've seen uses the TIMSI. Only an attacker would use the IMSI. It's not a solution, but at least it can make the targeted part a little harder. So what exactly does it do? So I'm going to get out of this. Actually, I have actually a BTS here. So I have a test GSM network running where I have connected several phones. So if I power on this phone, he powers on. Okay, you see that he registered on the network. Yeah. Yes, that's him. Okay, so if I try to call him right now, it should work just fine, hopefully. And it does. So that's kind of the expected behavior. Now I'm going to use an attacker phone here to transmit an IMSI detach message that will log off this phone from the network. So for this, I just start this. So here I'm loading the firmware, a modified firmware on this phone. Okay. Loading the firmware. And here I'm going to actually transmit the packet that's going to detach the phone. Okay, and it's been sent. So as you can see, the BTS, sorry, I'm pointing at my screen, but here has received an IMSI detach. And if I try to call this phone again, it should just not work. And it doesn't, call failed, because officially for the network, that phone is no longer on the network. So I'm turning it off now. How do you turn that thing off? Okay. Okay, so now we're going to talk about how you can use the same hardware, so still this mobile phone, to use as a passive listener. So first, what do I mean by passive listener? What do I want? I want the robust data. That is, as you saw in the beginning, there was 4 types of bursts. I want the normal burst, and I want those bits exactly, and not pre-processed or anything, because if you want to crack A5 or do other things, you really need that raw data. Preferably, I'd like uplink and downlink, because, well, it's better. And frequency hopping support, of course, because this is really used on real networks. So you definitely want support for it. The target hardware is basically what Osmocom-BB supports. This is, here I'm using a Motorola C123, but there are a lot of other models. They were chosen because it's a classic TI Calypso design. That means that first there was leaked documentation, so we're not completely blind, and there are a lot of phones available for it, and they're all very cheap, like €20 new, and you can find them for like €1 if you can wait. Why would we want to do that? Well, the debugging GSM project, like if you're implementing things like BTS or Osmocom-BB trying to implement new features, it's always really useful to know what's exactly on the air, because you can buy test equipment that does that, but this is very expensive, and being able to do it for like 20 euro would be really nice. It's basically a cheap USRP. It's kind of different, but the idea is the same. It has some advantage. Of course, it's much cheaper because the USRP is like 700 euro plus shipping and stuff. It would have hopping and uplink support, which airprobe doesn't support what's published right now. Also, it's much more portable. I mean, I have this always in my bag. I don't have my USRP all the time with me. Of course, it's kind of limited because the USRP is basically a wideband software-defined transceiver. It can do much more than what the phone does, but the problem is it's also much harder to code because you basically have to code everything yourself. For example, what's currently coded in airprobe, in particular the demodulator, it works, but it doesn't work as well as like the commercial demodulator that you would find in this phone that has been optimized for many years, and it works very well. So in general, everything related to GSM could use, a cheap sniffer. So this is what the reception path of this phone looks like. It's of course a little simplified, but that's the idea. Each element, we're gonna go through each element and see, can this element do what I want it to do? Is it an obstacle? And if it's an obstacle, is there some way to walk around it or change it or whatever? Okay, the first element is, well, the antenna. It's completely unremarkable. It's like a 0 dB gain. It's okay. It has poor gain, so it's okay if you want to receive the base station, because the base station transmits with a lot of power. It's also placed very high above the ground. It has great antenna, so receiving it is really not a problem. On the other hand, if you're trying to receive the phones themselves, they also have poor antenna. They only transmit like 1 watt maximum, and that's only if the BTS doesn't tell him to transmit less power. And also they're like at ground level, so receiving them is much harder. To try to work around that, you can either use like an external antenna or just preamplify the signal with a RF preamplifier. You have to be careful though, because if you since your amplifier or your antenna will amplify everything, you can saturate the input stage of the phone, and then you don't receive anything. Okay, the second element is the reception filter. Basically, to improve the quality of the signal received by the phones, the manufacturer put filters in there that filters out everything that's not in the band that the phone is supposed to listen to, which is great because it protects against all kinds of interference. However, it's bad for us because if we want to receive uplink, that signal is going to be attenuated by something like 30, 40 dB. So you have already weak signal, you're cutting 40 dB out of it, there is nothing left. So what can you do about that? Well, either you just don't care about uplink, that's an option, somewhat of an option. You limit yourself to lab testing only, because in a lab, I mean, if you're holding the transceiver phone in one hand and the sniffer phone in another hand, it's going to work fine. They're like 1 meter apart. The signal is going to be strong enough. But if you're like 100 meters away, that's not going to work. So the only real option is to remove it. It's kind of annoying because it's a hardware modification, but yeah, it's still better to do. Now, a couple of complications though. The filter does more than just filter. It also converts what's called an unbalanced signal into a balanced signal. So basically it's a single-ended to differential. So you can't just take the filter out and put a solder bridge in its place. You actually have to replace it by another component. And those components are like 2 millimeters by 1 millimeter. But you can do it. And the other problem is bias voltage difference. Basically, the input signal is like reference to the ground, and the output signal is reference to some internal reference of the preamplifier. So you have to make sure you use capacitors in the path, which again are like 0402, it's like very small. But it works. Just after that, you find the mixer. The mixer is basically the tuner of the phone. It can obviously tune anywhere in any downlink band that the phone supports. So even if, actually even more than what the phone supports, because the chipset itself supports like 850, 900, 1800, and 1900, even if officially it only supports like 2. The tuner will actually support all the bands. But it obviously doesn't support tuning into the uplink, because a real phone never has to do that. That was kind of a problem. So we just tried it. We took the formula in the datasheet, how to compute the PLL configuration values, and we applied them for the uplink frequencies, and we loaded that, and it just happened to work. Of course, it's outside of the spec, so the characteristics might be a little less good, but it works, and that's the main point. So we just removed the check in the code that checks if it's inside the specification, and just loaded the values. So the RF mixer outputs analog IQ signals, quadrille signals, into the analog baseband. The analog baseband is just basically an ADC. It converts the analog signal into digital samples that can be later processed. It doesn't really pose a problem for us. The only problem currently is the driver for it is slightly limited, because you configure it to receive like 160 samples. That is one burst, and you have to configure it for each group of 160 samples. And currently the drivers doesn't allow to configure 2 consecutive bursts. So that's a limitation, but that's a software limitation, because the hardware has to be able to do it, since it's a requirement for GPRS multi-slot, and this chip is supposed to support at least two consecutive bursts. So with a little work, we could just lift that restriction. Okay. The next step, inside the digital baseband, which is like the biggest chip on the phone, there is 2 subchips: the DSP that will do all the demodulation and things like that, and the ARM. So the DSP is ROM based. That is, there is a firmware. It's hard written. We cannot change it. What we can do, however, is like apply small patches, because the manufacturer didn't want to reburn a new chip each time. So there is a small area of RAM where you can overwrite small part of the ROM in sort. They use like function tables, and so you can overwrite entries in the function tables if you want to call your function instead of the default function. In theory, the DSP never gives you the raw burst. Yeah, I mean, the bits, the demodulated bits, it keeps them, and then it will apply like deciphering, inverse error correction, all convolutional coding. All that is applied inside the DSP, and what the DSP outputs is like a full layer 2 packet. In case of control channel, and for voice channel, it actually decompress the voice data inside the DSP and sends them to the audio codec directly. So in theory, you're not supposed to get the raw burst. So you have to patch it. Procedure is, well, simple, kinda. You just dump the ROM, which is in theory impossible. It's in theory copy protected, but you can work around that. And finally, you reverse engineer it, so you know how the ROM works. Hopefully, IDEA supports it. So after like long hours staring at the assembly of the DSP, you can figure out how it works, and in the end, write a custom task for the DSP that will do what you want. That is, get the samples from the analog baseband, apply the demodulation, and then sends the raw demodulated burst to the ARM without any further processing. And this is something that took a long time, but it's finally done, so that's good. Then you have the ARM processor. Osmocom-BB has drivers for almost everything in the ARM that we need, at least. It can drive the analog baseband and the mixer and everything. It also has all the logic for cell selection, cell synchronization, and what's called the TDMA scheduler, that is scheduling events on particular frames on the GSM network. There are a few things we need to change. First, we need to patch the DSP at the boot. That's kind of obvious. Finally, we need a driver for the new task that we added to the DSP. It's obviously not supported in the mainline code, so we had to write a driver that allows to program the DSP to use this new command and receive the raw burst. And finally, we never want to transmit anything, but instead, if we wanted, instead of transmitting, we want to receive, but instead of receiving on downlink frequency, we want to listen to the uplink frequencies. So the changes in the ARM code are actually pretty simple. If you're familiar with the Osmocom-BB code, I would say. Yeah. Finally, we have to get the data out somehow. Osmocom-BB uses a serial port, which is the advantage is it's very simple. However, at 115 kilobaud, it's just not fast enough if you want to receive like 2 bidirectional voice channel. You have to receive like 4 bursts of 160 bits, and we transmit soft bits and not hard decisions. So it's a lot of bandwidth. Not much of a problem. We can just increase the baud rate. The only complication is that the standard cable that everyone uses is based around like the PL20 something USB to serial controller, and that controller doesn't support non-standard baud rate, so we have to use the FTDI ones. It's slightly less practical because it looks like that, but yeah. It's still very cheap, and the advantage is we get like 4 serial ports in one board, so we can control 4 phones at once if we wanted to. Okay, I'm gonna show you what it looks like. So okay. Okay, what I'm going to do is I'm going to place a phone call from, let's say, this phone to this phone. And using the sniffer phone, I'm going to record the uplink and downlink of this one. Of course, I will have both sides of the conversation since I'm listening to both uplink and downlink at once. So I'm loading my modified firmware inside the phone. What the sniffer application does is it listens to the assignment channel where the GSM tells, okay, you go to that dedicated channel, and switches to the first assignment it finds, listen to it, and up until there is nothing left to listen to. Okay. Okay. Yeah. Okay. So here I'm talking into the call, the phone that's making the call, so I will hear this voice onto the uplink channel. If I'm talking onto the receiver phone, I should hear what I'm saying in the downlink channel of this phone, since this phone is receiving it from the network. Up, and it shuts down. Okay. Okay, so what the sniffer application did is save all the data inside a file that contains all the bursts that have been recorded. And I'm going to take that and take it through a program that will take the burst and extract the voice data from them. So if I look like, in theory, if I look like here, okay, it created this file, which is 1428 RFC and 876. If I remember where the program is. Okay, main. Okay, so it processes the frame. For each burst, it displays what kind of data it found. Sometimes it finds nothing, sometimes it finds control data or things like that. But for the voice data, it created, in theory, if I put it in full screen. Okay, yeah, it created those two files, speech DL and speech UL, which correspond to the speech channel for the uplink and the speech channel for the downlink, obviously. I can now play those. You'll notice that there is silence at the start because it actually transmits silence when I haven't actually answered the phone yet. Yeah. Hopefully.
I'm talking onto the receiver phone. I should hear what I'm saying in the downlink channel of this phone, since this one is receiving it from the network.
Okay. So this was the downlink channel, and as you said, you heard what I said, and of course the uplink channel is the same, but for the other channel. Okay, going back to the slides. Okay, so very short summary. Basically, GSM has definite protocol flows. That's very clear. The attacks are both very simple in principle and very cheap to implement. So you can only imagine that if more people spend time, working on this, what they could possibly find on this, and now with the hardware that exists and the software. Sorry. It becomes very, very easy. What kind of stuff could you do in the future? Okay. One problem that happens a lot if you try to listen to a commercial network is that the phone doesn't directly go to the voice channel. It's sent to a control channel, and then the ciphering is enabled, and when the phone is actually answered, you get switched to a voice channel. This has caused some problems if you want to actually listen to the voice calls, because the assignment to the voice channels is transmitted in ciphered, so you'd have to crack it very, very fast if you want to follow it. But instead of just following the assignment of the network, you can monitor the transmission power that you detect on those frequencies, and you will see clear. If the cell isn't too busy, you will see that you have RF power, and then it drops when the channel is cut, and then when it's assigned, you see that it rises again, and that allows you to break like the hopping sequence and stuff like that by just analyzing the RF power if the cell isn't too busy. One problem with this approach is what's called discontinuous transmission. Basically, to save power both in your phone and in the network, when there is nothing to transmit, like silence, it doesn't actually transmit anything, so you don't detect any power at all. Hopefully, there is always a control channel that's associated, and this one is always transmitted, so you can always monitor that. There is less data on it, so you have less data points to find the assignment, but I think it should be possible. That's something to try. Something else we've started to working on is using a phone as a BTS, because if you want to experiment with like the network, we now have Osmocom that can run on very cheap phones. But if you want to fuzz like your iPhone from the network, you still have a bit of investment, because you have to either get a USRP to run like OpenBTS or NanoBTS or BS11, but those are hard to find now. And they aren't cheap. I mean, a NanoBTS, like it's on the floor here, it costs like $300,000. So, 3,000, sorry. Yeah. So if you could do it with a 20 euro phone, that would be great. And I think it's possible, at least using 2 phones. Definitely something we want to look into. And so some other people were talking about using direct phone-to-phone communication. That's also something you could probably easily do. And whatever you can think of. If you find something that you think is interesting, and please research it and read the spec and see if it's really possible and try to implement it. It would be great. A final thanks to basically everyone that contributes to open source GSM projects. And the most notable names, of course, Harald Welt, Dieter, David Burgess, that works on OpenBTS, Carsten Noll for the A5 project, and Olger, that works a lot on OpenBSC, and Andreas, who has like almost single-handedly implemented the mobile application on the upper layers of Osmocom-BB. Also thanks to the NLNet Foundation, who funded part of this work. Here is some reference that you can read. Basically, the airprobe project, if you want to use the USRP to listen to traffic, Osmocom-BB for the software that runs on this phone. Also note that the sniffer code is in the Git now. It might not be the latest version, but I will push the latest version soon. OpenBSC, OpenBTS, and finally, please read the GSM spec if you're interested, because it might be a little intimidating because there is like a lot of specification, but you don't have to read them all. There are a few pointers in the beginning of what specification you could read depending on what you're interested in. And that's it. Thank you for your attention. Does anyone have any question? Yes?
I have a question is to clarify the MC Detach dose. Can you actually send the MC and not the TMC on from anywhere in the network, or do you really have to be in the location area? Or
Okay, from what I've tested, it's on the location area, but I only tested on like 4 networks. I don't know, maybe there are some bad implementations. The specification doesn't really say that you must check, but it seems obvious that you should. So.
And did you try on all the networks you tested with the TMC and both TMC and MC, and do they all accept
I actually only tested with the IMSI, because each time I didn't know my TMC. Okay. But I know that the phone sends the TMC, so it should work with the TMC as well. But I tested with the IMSI, yeah.
Okay, thank you.
Did you try to make the same exercise that the second one that you did with the voice which is encrypted with A51? And if you did it, how long it would have taken to get the voice when it's encrypted?
I dumped bursts that were encrypted. It wasn't voice, but it was control data. Now since you get basically the same data out of this program as you get from airprobe, the time to crack is exactly the same. So it will heavily depend on your machine. In general, it takes like, you need 8 bursts of known plain text, and it takes, at least on my setup, it takes like 1 minute by burst to break it.
Okay, so the same demonstration with the call which is encrypted with A51 would be decrypted in the same amount of time. You could have done the demonstration with the call.
Yeah.
Okay, thank you.
When you try to record, just to be sure, A51 encrypted calls, if you try to break the key, you will just have the possibility to read the control channel and get the voice channel assignment after you break the key. So if the call is long enough, you will have the possibility to jump channels, but otherwise you would lose at least 1 minute of you may lose at least 1 minute of call, if I'm not mistaken.
Exactly. That's a problem that you would face if you're trying to listen to a voice channel on a commercial network right now, is that you don't know where to go. So that's why trying to monitor the channel with the RF power would be interesting. The other option is on small cells, using like several phones, you can actually continuously dump every voice channel. And then afterwards, once you know what you should have listened to, you can just...
How many channels are there?
You have 8 time slots. Okay, it depends a lot of the cell, but one frequency can host 8 time slots. And some cells have only 1 frequency. Others have like 33, so that's get a lot. And a phone can record 4 time slots per frame.
Thanks.